Hello, this is the brief review of the chapter on correlations, effect sizes, and confidence intervals. Now, correlation is different from really anything we've done so far. All of the statistics that you've looked at and learned so far have really compared a sample mean to something else. Sample mean to some population mean, sample mean to some other sample mean, or some combination of sample means. Correlation, of course, is very, very different. You're not comparing sample means at all. In fact, you're comparing variables. You want to know what the relationship is between two variables. If um, if you measure two variables for a given person, for example, do those variables tend to have similar scores or opposing scores? What I mean by that is, does if someone has an above average score on one variable, do they also tend to have an above average score on the other variable? If so, that would be a positive correlation. If they have a above average score on one variable and then a below average score on the other variable, then that would be a negative correlation. So again, what we're looking at here is how scores on two variables co-vary, how they change based on the other. So if you know one variable, can you reasonably predict what the other one is likely to be? If someone's going to be above average on one, does that give you a better than average chance of choosing whether their score on the other variable is above or below average? If you can, that means that there's a correlation that's useful. Now, when do you use these correlations? It depends on the types of variables you're comparing. You have two different correlations. You have a Pearson correlation and a Spearman correlation, and both are comparing two variables, but you're going to use a Pearson correlation when you are comparing two variables, not comparing, but examining the relationship between two variables that are interval or ratio. If both are interval, then you're going to use Pearson. If both are ratio, if one is interval and one is ratio, in all those situations, you're going to use Pearson. Spearman, you're going to use if one of the variables is ordinal. So if one is interval and the other is ordinal, Spearman. If one is ratio and one is ordinal, Spearman. If both are ordinal, Spearman. The other situation you're going to use a Pearson correlation is when you have a scatterplot that looks linear. And if the scatterplot doesn't look linear, it's nonlinear but monotonic, then you'll use Spearman. And I'll show you a graph of this later in the slides. Now, the logic of correlation, it really comes down to z-scores. As I alluded to before, if both variables if one variable tends to be above average and the other one tends to be above average, then they're both going to have positive z-scores, and then you're going to get a positive r. If one variable tends to be above average and the other tends to be below average, then you're going to get a negative r. If there's really no pattern, if one is above average and it doesn't allow you to reliably predict whether the other one is above or below average, then you should get an r close to 0. So again, what you're looking for here, I'm going to get my pointer out. What you're looking for here when you get the correlation is the direction of the association. And again, if it's high and if one variable tends to have a high score and the other one also tends to have a high score, that's going to give you a positive correlation. If one variable tends to have a high score and the other one has a low score, that would give you a negative. So that's the direction, positive or negative. You're also going to look at how strong the trend is that you've noticed. And again, the correlation coefficient is going to range from -1 to +1, and the strength is indicated by the distance of the correlation coefficient from 0. So a +1 and a -1 are equally strong because they're equally far from 0. Of course, weak associations, weak correlations are going to be close to 0. If the null hypothesis is true and the two variables are not associated at all, you would expect an R value close to 0, of course. Now, the correlation coefficient is going to change a lot based on the scatter plot, obviously, because it's analyzing that data. But if the scatter plot has certain problems, then the correlation coefficient is going to be misleading. So you want to look at the scatter plot before you really interpret the correlation coefficient, because if there's a problem in the scatter plot, then you will need to address it somehow. So first, let's look at some scatter plots without problems to see what you're looking for. This correlation up here and this scatter plot up here. Let's first describe what a scatter plot is. So this would be the x variable, the first variable, and as a score, it's like a number line. So 0 to whatever the top score is here, and then your y variable goes to the vertical axis, 0 to whatever the high score is here. And each data point is a given person's paired score. So this person had an x score here and a y score here. So that point represents the combination, the pairing of their two scores. And so each dot represents a person. Now, when you look at the whole scatter plot, this one looks like a big basketball, looks like a big circle. When that's the case, you're going to have a correlation of 0. There's no linear trend here. It just looks like a big glob of scores. This one over here is another example of a 0 correlation, just a big clump of scores. There's no linear trend. Now, when you go down to this next level, you can see there is some flattening. There does seem to be some linear trend. It looks more like a football than a basketball. This one's leaning to the right, and this one's leaning to the left. So this is a positive correlation, because as x scores go up, y scores go up. So that's positive correlation. This is a negative correlation. And you notice the width here, the width across how flat it is, indicates the strength of the correlation, or the strength of the correlation, the strength of the association. The flatter the linear trend, the more it forms, the more it's organized into a straight line, the stronger the correlation. So here, as you move down to the next level, see this is quite a bit stronger. Again, it's positive, it's leaning to the right. This is negative. And then down here, you have a perfectly linear association or correlations of +1 and -1. Notice how the points never deviate from a perfect line. Now let's look at some scatter plots that indicate some potential problems. This first scatter plot represents an outlier. We have one score that is very different from the rest. See, we have a clump of scores, and then we have this one that's kind of far away from it. That looks like it might be an outlier. When you have an outlier like this, you're going to want to maybe try and identify if it's a data entry error. So go and try and find that point in your data set and see, is there some obvious mistake that was made when you were entering the data? If so, fix it. If not, then if there's no good reason for taking it out, you would just analyze it, but realize that this outlier is going to have a very large effect on the correlation coefficient. And so when you interpret it, you're going to want to think about how to interpret it, because if this one point changes the correlation a lot, then the relationship might not be that reliable. This next graph is reflective of a ceiling effect. You can see that there's a lot of points that are flattened out at the top of one variable, and that's a ceiling effect. You might also get a ceiling effect where they're flattened out against this right edge. You could also get a floor effect where they're flattened out down here or flattened out over here. When you have a situation like this, that means the correlation coefficient is probably going to be suppressed. It's going to be smaller than it might be in the population, because you have some response compression. You have some you have people who might be able to score higher, but your dependent variable is compressed. It doesn't allow them to score higher than that. If, for example, you're giving an exam and a lot of people are getting 100%, you're not measuring individual differences in ability very well, because if the test were harder, a lot of these 100 would separate out, and there'd be fewer 100s, and so you'd be able to tease out who knew the material better at that high end. So again, if you see something like this, you should consider that the correlation might be a little bit compressed. It might be smaller than it really is in the population. This scatter plot over here is representing heteroskedasticity, which is a potential problem, especially when you do something like regression. We have one activity on regression, which we may do. Heteroskedasticity specifically is the fact that if this is your x variable, look at the variable of 2. The range of scores for an x of 2 is about 1 to 3 or 4, right? So it has this amount of range. So again, at x of 2, the range of y is about this much. However, at an x of 10, the range is quite a bit longer. There's a bigger range. That's heteroskedasticity. You have more variability at certain levels of x than you do at other levels of x. And that creates a problem for regression that we'll talk about when we do the regression activity. So again, look at the scatter plot and you're aware of that problem. You can perhaps address it. These bottom 3 scatter plots are meant to help you differentiate when to use Pearson's correlation versus Spearman correlation. In a previous slide, I indicated that one of the criteria used to choose between the two is whether the scatter plot looks linear. This is a linear scatter plot. There's just no bend in the data. It's pretty strong correlation here, but that's really not the indication that you need to use Pearson. The indication is that there's no bend or trend in the trend. Here, there's definitely a bend in the trend, so that means you want to use Spearman. And here there are 2 bends, and that's too much. So that means you can't really do either. So you shouldn't use either Spearman or Pearson correlation. But if there's just one bend, it's called monotonic. It's nonlinear but monotonic, just one bend. That means you can use Pearson. Now the example we're going to use to illustrate correlation is the question, are procrastination and college GPA associated? So these are the 2 variables we're dealing with, and we want to know if one person has a high procrastination score, do they also tend to have a high GPA, a low GPA, or is there no association between the 2 variables? So the study here is very simple. You're simply giving a bunch of volunteers the scholastic procrastination scale, and then you're collecting their current GPA and going to see if there's some association between these 2. Again, a very simple correlational design. A previous study by Richardson and his colleagues found that there was a negative correlation between these 2 variables of about -0.2. That's a small medium effect, if you can see at the chart over here. And so that means when it comes to determining your sample size, you're going to want something greater than 85 as your sample size, because the effect you're trying to find is a -0.2, but you can ignore the sign when you're talking about the size here. So you're going to want something, you want to be able to detect an effect of about 0.2. You want to be able to find that. So you're going to need something larger than 85. Now, a 0.1, notice how the big jump when you go to 0.1. This is closer to 0.3. So somewhere, not quite in the middle, but a little bit more than 85. We got 98, which is reasonable for this study. First pillar, of course, is hypothesis testing with a continuous p-value, and the first step is to choose the correct test statistic. And as we've talked about previously, with correlation, what you're looking at is the scale of measurement that the two variables are measured on. If both are interval or ratio, then Pearson. If one of those is ordinal, then you're going to use Spearman. In this case, we're looking at the relationship between people's score on the scholastic procrastination scale, which is an interval scale, and college GPA, which is a ratio scale. So that means that we are going to use Pearson correlation here, assuming the relationship between the two is linear and the scatter plot doesn't look funky in any way. But we'll do that when we get to the graphing. So the next step is to assess the statistical assumptions. Data independence is the same here as it has been for everything else. One person's score shouldn't influence another person's score. Appropriate measurement of the variables, we've already talked about that. In this case, both of them are interval or ratio, so Spearman is not appropriate. We want to use Pearson, I should say, because again, both of them are interval or ratio, so Pearson correlation. And then is the relationship linear? So we examine the scatter plot here, and it doesn't look like a very strong relationship, but it is. There's no bend in it. So yeah, this looks linear enough to run a Pearson correlation. And then homoscedasticity. There doesn't seem to be any evidence of heteroscedasticity here. You know, it's not perfect, but there doesn't seem to be. It looks more like a ball than it does a big fan, like the heteroscedasticity graph that I showed you previously, where it's very compressed at some values of y and then gets really wide for others. This looks more just like kind of a big ball. So not really compelling evidence for heteroscedasticity here. Next step is to identify the statistical null hypothesis. And of course, if there is no effect, that would mean that the two variables are not associated with each other. And if there is no effect, that means you would expect an R close to 0. And then that would mean that if there is no effect, that any deviation from an R being of 0 would be due to sampling error. The fourth step is to graph the data, and we've already done that. But again, as in previous chapters, if you look at the graph, it'll give you some indication of the type of results you should expect. As I look at this graph, it looks like it's going to be a weak relationship or smallish relationship. Again, previous researchers found a negative 0.2, so that's a pretty weak relationship. And this looks like to be maybe a little slightly negative trend. You can see a line of best fit here suggesting that it is a negative trend. So you're expecting a small negative trend is what you're going to expect with the correlation coefficient. Step 5 is to actually compute the correlation coefficient and then interpret its p-value. Again, we're going to be more interested in you interpreting these values than crunching the numbers by hand. In this case, if you did crunch it by hand, you'd get a negative 0.2. And again, previous research got a negative 0.22, so we're pretty close to what they got. We're going to do a two-tailed p-value here. And so the p-value is 0.047, and now the next step is to interpret that p-value. So a p-value of 0.047 literally means that that's the probability of getting an R value of plus or minus 0.2 or more extreme, further from 0, if the null is true and there's no methodological flaws in the study. So this is fairly compelling evidence that there is a at least weak association between procrastination and college GPA. So that means this is compelling evidence against the null hypothesis. Specifically, we can conclude that these data suggest that the relationship between procrastination and college GPA is negative in the population, and it has a small medium effect size. We'll talk more about the effect size in the next slide. So the way you interpret effect size with R or correlation, there's a couple ways. You could just look at the R. Here is the guidelines for interpreting R. 0.1 is small, 0.3 is medium, 0.5 is large, so we got a 0.2, so we're right between small, medium. We can also interpret the effect size by converting R to R squared. Obviously, you just square it. In this case, that comes out to be 0.04. That means that 4% of the variability in procrastination score is explained by GPA. Or another way of saying it is GPA, variability in GPA explains 4% of procrastination scores. So in other words, one variable explains about 4% of the variability in the other variable. Now, 4% again is about a small medium effect. If it were perfectly correlated, it would explain 100%. So again, 4% may not sound like that big, and it is a small effect, but consider a large effect is 25%. If you could explain 25% of another variable's variability with, say, a variable 1, then that would be considered a large effect. So again, here we have a small medium effect of, in terms of the relationship between procrastination and college GPA. Now we can estimate the population parameter with a confidence interval. Correlation coefficients are not normally distributed, so that means computing a confidence interval around them is a little more complicated, or at least it involves an additional step that was not necessary for any of the other confidence intervals we've created in this class so far. What you have to do is you have to take the R and convert it to a Z, then compute a confidence interval around Z, and then take that Z that you just computed and convert it back to an R. And so that's what we've done here. Again, I'm not going to go over the computation here. That's described in the chapter, and if you're interested, I'd be happy to talk to you about that. But the point here is for you to remember 2 points. First, you have to remember that there's an extra step. You have to, if you're computing a confidence interval, you or the computer is going to convert that to an R, convert that R to a Z, then find the upper bound and lower bound for that Z. Then you're going to convert that Z back to an R. And that's what's been done here. So this means that the strongest correlation that's plausible for the population between these two variables is a negative 0.38, and the weakest one that's plausible in the population is a negative 0.003. So a negative 0.38 would be a medium large effect. That'd be pretty big correlation, and this would be obviously almost negligible, almost nothing. So again, we have a pretty wide range, which suggests that if you want a more precise estimate, you probably want a bigger sample size. Again, our point estimate was about a 0.2, negative 0.2. That's probably going to be the best guess, not only because it's our point estimate, but some other researcher found something close to negative 0.2 as well. So that should build your confidence that that point estimate may be pretty close to the mark. Of course, as with other statistics, you need to consider the methodology that was used to collect that data. In this case, we had a pretty simple design. We simply gave somebody a questionnaire and then collected their college GPA and correlated them. So we have very limited confound control. We don't really know if procrastination causes a low college GPA. We know that they're associated. So we would need additional research to support a causal conclusion here. We just know that they're associated. Now we need to consider the scientific literature. And so we want to compare our results to what others have reported in the literature and then offer our own interpretation. I've indicated several times that previous researchers did find a negative correlation, very similar to what we found. Again, so that should increase our confidence in the reliability of our data and really increase the confidence of readers' interpretation of our data as well. We'll also want to offer our interpretation of this data and how it might be used, what future steps might be for other researchers. And of course, the final step is to provide your scientific conclusion. As with all the previous chapters and statistics we've talked about, you really want to do 6 things. You want to say what you did. In this case, you're not really comparing means, but what you are doing is exploring the association between 2 variables. So you want to tell you what you're doing and how, the statistics, interpret the p, the effect size, the confidence interval, and then comment on the methodology. So in this case, we ran a Pearson correlation to test the relationship between the measure of scholastic procrastination, the SPS, and college GPA. So that's basically what I did. That's the statistic I ran and the variables I was comparing. Then I provide the statistics, the mean for the SPS and the standard deviation, the mean for the GPA and the standard deviation. I ran an R. 96 is the degrees of freedom, which is the number of people minus 2, so there were 98 people. Here's the correlation, here's the p-value. Notice I'm telling them it's two-tailed, and here's the confidence interval for R. Next step is to interpret the p-value. The observed modest negative association between SPS and college GPA probably did not result from sampling error. That's because of this. Again, the p-value is 0.047, so that rounds up to 0.05. And that's right on the borderline of what's conventional, but that's compelling evidence that there is a small negative association between these 2 variables. Next, we want to talk about the effect size. So then we go, the evidence suggests that a modest association between scholastic procrastination measured by the SPS and college GPA. And then I just inserted R squared there. Just this R squared. Now I want to talk about the confidence interval. Based on the present study's statistical sensitivity, the magnitude of the procrastination's relationship with GPA in the population could be negligible, it could be essentially 0, or it could be as large as an R squared of 0.14, which would be a medium large effect. Where did this come from? Well, this is this upper bound R value squared. Again, I'm interpreting the confidence interval there. Finally, I want to comment on the methodology. The present study's design cannot support the conclusion that procrastination causes lower GPA. Future research should explore this possibility. I'm just commenting on that. That's maybe obvious, but it's something to throw in about the methodology. You shouldn't say that, oh, gee, now we need to teach people to not procrastinate, and then their GPA will go up. Well, GPA, the relationship between those might not be causal. It might be, but we don't know. So we can't really say that statement. It's good to remind people of that every now and then. This is a solid scientific conclusion based on the data presented.